So to get into Excel, you're going to go down to kind of the home menu and you're going to open Excel as an application. It is loaded on all of the computers here in the lab and at LTC. So you have, a lot of availability to it. And then you're going to just open a blank worksheet. So you just click on that. Now, so that you can see what I'm doing, what I am going to do is just zoom in here so that the cells are a little bit larger. Okay? Now, I know on the screen, the overhead screen, it's not as easy to see, but truly you'll see them populate. What we've got going on here when we open up Excel is we have these cells. Each one of my squares here, or my rectangles, is called a cell. And the cell designation is going to be given by the column and the row callout. So the cell that I'm in right now is A2, okay? If I go over a couple, I'm in D2, all right? So first the column and then the row. Now, I can move around in my cells by either clicking with my left mouse button in whatever cell I want to go to. I can use the up, down, left, right arrows, or I can use the enter key also, okay? So you can move really easily, around in each one of those cells. Now, to populate the cells, if I just want to put words in there, like give it, if I'm going to be giving a label to a column, for instance, like I'm going to put variables, okay? I can just literally click in there and I can start typing, hit enter, and it populates, okay? Now, I can also put numbers in. So let's say 12. I just enter that number in there and I hit enter and it's populated into that cell. But the power in Excel comes when we write actual equations into the different cells. So what you can do to start off the cell here to get in kind of that equation or formula mode, we're going to hit the equal sign, okay? And then that keys this up that, oh, you're writing an equation now. You're not just going to be putting text in, okay? So the equal sign is going to be the hint that's going to let us know that we're going to be putting an equation there. We are going to be converting over some of the equations that we learned throughout the semester into this format, okay? Back in statics, we did a spreadsheet unit. That was it was our last unit as well. And so there's some things we're going to build on there. Some of the things you might have to refamiliarize yourself with depending on how often you use Excel or are around it. But we're going to kind of use that as the basis here. And so we're going to be doing some more problems to practice the applications of. Okay, so we will get back over here in a little while, but that's going to be what we're going to be writing our programs for. So as we go to our assignment sheet for the spreadsheet unit, the first 3 problems here are out of Chapter 12, which is the torsional shear stress unit that we had earlier in the semester. We're going to be writing 3 spreadsheets. The first one is going to be for example 12.3. Next one is going to be example 12.7, and then the third one is going to be for problem 12.14, which is one that you did for me as an assignment. Now, what I did do was print out from chapter 12, I printed out the kind of that equation sheet that we had at the beginning. It's a handout. If you don't have it available, you can go back to chapter 12 and simply print out this handout. And the second sheet of the handout is a summary sheet of all of the equations that we used, okay? So it's a nice reference for these first 3, okay? Now, what I'm going to do is I'm going to start by opening up to page 271 and looking at example 12.3 as a problem to see how we're going to approach this as we start to determine how we're going to set up our spreadsheet to solve it, okay? So example 12.3 says we want to find the shearing stress on the outside and the inside of a hollow circular shaft with an outside diameter of 6 inches and an inside diameter of 4 inches. And they're telling us that the torque is 20,000 pound-feet. What is the angle of twist when the length is 15 feet? And then they're giving us the G is equal to 12 times 10 to the 6th PSI. Okay, so the reason I have the example problem here is so that you can kind of follow along, and as you do your spreadsheet and you are testing out your programmed cells, you can make sure you're getting the right answers. Okay, so that's why we start out with some example problems here. Now, we want to find the shearing stress. So as we look back at the equations we have for this unit on that sheet that I just showed you, shear stress, we have this base equation right here. Shear stress is going to be the torque times the distance out from the center of rotation to the outermost material divided by the polar moment of inertia. Okay? Now, as we look here, and I'm actually going to pull up the previous sheet. When we look at torsional shear stress, as we are twisting on an object. So if we look straight down on it, you might remember this illustration. So this is the center, okay? This is going to be the rotation that's occurring. And so you'll notice that as we move out towards the outermost material, which we call dimension C, okay? That is where the application of the maximum torsional shear stress is going to lie, okay? As we move at any other radius, okay, it's going to be dependent on that radius. So the further we go out, the greater the torsional shear stress gets. The closer we get to that center of rotation, the less it gets, okay? So whether I'm calculating the max or any of the torsional shear stresses along the way. So when I have a hollow tube that has a wall thickness, this is going to lie at a radius dimension on the inside diameter, and the C dimension is going to be to the outside diameter. Does that make sense to everybody? So our base equation, whether we are looking for the maximum or if we're just looking for a value of torsional shear stress, this can be substituted with an R for the radius to get whatever the torsional shear stress is at that location. Okay, so we're going to do this twice. We're going to do it once for the outermost material to the OD where the max is, and then we're going to do it a second time so that we can find out what is the torsional shear stress on the edge of the ID. So this one is going to be a radius, and this one is going to be that C dimension. Does that make sense to everybody? Okay. All right. So with that, I'm just going to kind of look at this equation. So knowing that we're going to be calculating this twice, we already are given the diameter for the inside and the outside, so we can calculate what that C is. We were given the torque, okay? So what we also need to find is our J, our polar moment of inertia. Polar moment of inertia is going to be a cross-sectional area's ability to resist twisting, okay? So polar moment of inertia equations are up here, solid shaft and a hollow shaft. Hollow shaft is what we're going to be looking at. So OD, ID. So we need to put a cell so that we calculate our J. And then we're going to reference it in that equation. Okay? So let's kind of follow this example through so that we understand the approach that we're going to be taking here. Now, I am going to highlight the inputs. They gave us the outside diameter of 6 inches and the inside diameter of 4 inches. They gave us a torque equal to 20,000 pound-feet, and then they want us to find the angle of twist at 15 feet, so we have a length, and then we also have our shear modulus of G equal to 12 times 10 to the 6th. So that is what I'm going to kind of list as given or input variables when we look at it on the spreadsheet. So I know that my outside diameter, inside diameter, so OD, 6 inches, ID, 4 inches, capital T torque is 20,000 pound-feet, and my G is equal to 12 times 10 to the 6th PSI. Okay, so I just kind of did that. Now, I know that I need to get to, and I'm going to give myself a little bit of space here. I know I need to get to, as a final answer, tau max and tau on the ID, okay? I know that this is going to be T times C divided by J. this is going to be T times R divided by J. Okay? Now, the torque I already know. The C I can calculate from half of 6, right? This is the diameter. Okay, that's OD, so that's a diameter for each one. So the radius, or the C, is going to be 3. And my J I need to calculate based on my J equation. So I am going to say that J is equal to pi times the OD to the 4th power minus the ID to the 4th power divided by 32. Okay? That's my base equation. Now, what I want to do here is I want to write it out the way I would put it into a cell. I can't write it top to bottom, like I would normally. Okay? So we practiced this last year in statics, or at the end of the statics class. So when I put this into my cell, I'm going to select a cell. Okay, I'm going to put my cursor in that cell. And the first thing I'm going to start with is the equal sign. Okay? Now, I have to remember my order of operations. Okay? I know that anything that's in parentheses is going to be done first. And I know anything that is going to be a multiplier or a power is going to have precedence over a plus or a minus, right? Okay, and then I work left to right. So as I look here, I need to do the top, and then I'm going to divide by 32. Okay, now I'm going to start off with, I'm going to be putting pi in place. Now you can either use the function pi, or I find it just easier to write 3.1415 is going to be the value for pi that I use. Then I need to do a multiplication sign, is used as an asterisk, okay? And then I am going to use my first parentheses here. Now, I'm going to use the diameter for the OD. So, just like we do in the spreadsheets that you use in other classes for me, I am going to have this 6 in a cell, okay, up at the beginning of the spreadsheet as like input that I'm going to be putting. Same thing for the 4 inches, the torque, and the G. Okay, those are given variables for me. So down here, I am just going to put diameter, OD, but this is going to be a cell that I reference where I put my value of, in this case, 6 inches. The beauty of a spreadsheet is that I can change it to whatever I want. That's going to be like something I'm going to put in, and if I want to change it to 8, then it's going to update all the information for me, right? So my DO. Now, I need to take that to the 4th power. So I'm going to use this, like, I don't know, I think it's called I don't know what it's really called, a caret? I call it a caret. But it's actually putting this to a power, and I'm going to put the number 4 in back of it. Okay? Does anybody know what that's called? I don't know. I'm calling it a caret. It's on your keyboard. All right, and then I'm going to do minus DI, which I call the ID. That's also going to be a cell designation. And I'm going to take that to the 4th power. Okay? So it's going to be that little caret with the 4 in back of it. Now, I need to close that parentheses. If I ever start a parenthesis, I have to close it. So pi times DO to the 4th minus DI to the 4th. Now I need to divide this by 32. So I need to first have the entire top line done before I divide by 32. I don't want to do part of it, divide by 32, then multiply by pi. That's not the operation that I want. So to ensure that, I'm going to put parentheses around the 3.1415 and then the very end. One thing to always remember as you're doing this, Excel will call an error if they don't see you close the parentheses. Okay, so it won't let you do it. So always make sure that if you start a parentheses, you have to have a pair that goes with it. So I do. And then I'm going to do divide, which is that slash, and then the number 32 underneath here. Okay, that'll be fine. And then that will close my cell. This is how I'm going to write it in my cell designation. Again, referencing these two from whatever that input cell would be that I use. So that's going to be my J, okay? So I will have that calculated, okay, and this one too. So now I'm ready to create my equation for my maximum torsional shear stress in this type of format, okay? Now, I'm going to start, this is like being in my cell, so I'm going to start it with the equal sign. And I'm going to do the top of my equation first. So I'm going to do my T. Now my T is going to be an input. It was given to me in the problem. So there's going to be a cell that's going to have 20,000 in it, but it's in pound-feet, okay? Now as I look here, my J is in inches, my C will be in inches. So I am going to convert this to pound inches. Now you can leave it in pound feet up here. And we know that to convert it to pound inches, I know that 1 foot, 12 inches. So that means as I multiply across the top, divide by the bottom, I'm going to have to multiply by 12 to get this into pound inches, right? Okay. You could either have pound inches as your units up here, so you have to do it before you start the problem, or we can leave it at 20,000 pound feet, but when we're down here, we're going to say T, which is going to be a cell designation again from above, and we're going to say times 12 so that it can convert it right away to pound feet. I'm sorry, pound inches. Okay, so I'm going to put a parentheses around that. Then I need to multiply it by C. C is going to be the radius to the outermost material to the OD, okay? So this is a diameter. Don't multiply it by that, but you're going to multiply it by DO divided by 2, right? Because that's going to be the radius to the outermost material, and then put parentheses around that. This is also another cell designation. Now, that's my top line, so I want to put parentheses around that top line one more time so it does all of that first. And then I'm going to divide by J, okay? J is going to be another cell designation wherever I did this one. Does that make sense? Okay, I'm going to reference that cell where it calculated J. And then that'll be that one. Go ahead and write it for the ID. Okay, it's going to be similar, but just a little bit different. Okay, there's one thing that's different here. And then we can compare. How did you do? Everything's the same except this cell right here. What cell is that going to be? The DI. It's the ID dimension divided by 2. Okay? Now, the problem said we want to find the shearing stress on the outside and the inside of that hollow circular shaft. So that's what we have here and here. We just did that portion. Now we need to do the angle of twist at a 15-foot length. Okay? So angle of twist. The equation for angle of twist is right here. okay? It's going to be the torque times the length divided by G divided by J. We have all of it, don't we? We have all of it. Now, the thing that we need to remember is that this is in radians, okay? That's in radians when it comes out of this equation. So we then need to convert it to degrees. So let's first write this out as we see it. And I'm just going to start a new page. We know that our angle of twist is going to be equal to TL over GJ. So in my cell designation, okay, I'm going to start with that equal sign to get me in the kind of that function or that formula mode. I'm going to start here with my torque. Now, as I look here, my G I know is in PSI. My J is already in inches. My torque, I know I can get it in inches by just multiplying it by 12. And my length is 15 feet, so I have to multiply that by 12 too. Okay? So to start off with, I'm going to do torque times 12 to get it into pound-feet like we did on the previous one, right? So I'm going to put parentheses around that. Times length, and that's going to be given in feet from the problem. So you're going to use those same units, times 12 to get that in inches. Everybody kind of understand how and why I did that? Now that's my top line. So I'm going to put parentheses around that top line to kind of segregate it. And then I'm going to do a divide by. And now this is going to be G times J. Parentheses around that because that has to be done. Okay? Now, torque will be a cell designation. Length will be a cell designation. G is part of our input. That's going to be a cell. And then J will also be a cell that we would have calculated earlier, right? Kind of in our progression as we go down. Now, this right now is in radians, right? This right now is in radians, right? Whatever number I get, it's in radians. So to convert radians to degrees, we know that there are 2 pi radians in 360 degrees, right? So radians will cancel top to bottom. So do you see how I have to do this conversion up here? Now, I'm going to take all of this, the entire thing, okay, from the beginning to the end. And then I'm going to multiply that by 360, okay, and divide, I'm going to run out of room, by 2 times 3.1415. That's pi. Okay, I'm sneaking it in. Let me see. Oh, so mad at myself. 2 times 3.1415. Okay? Now, parentheses wise, I need to put parentheses around my 2 times pi. Okay? And then again around, between, and then again around 360 and the pi. Okay? Does that make sense to everybody? Can you kind of see what's happening there? When we input it into the spreadsheet, I think you'll kind of see that. All right. So let's go to Excel and see how we're going to put this in. All right. Open up Excel. All right. So I have a blank sheet here right now. Now I'm going to set mine up the very same way that I do it for the other classes. Most of you have me for machine elements, and what I do is you can give it a header up here, and I'm just going to kind of start over and to the right, because if you want to put some additional information like your name or the problem number or whatever information you can put up there. But I'm going to start out by my first column. I'm going to call it variables. And this is just giving each one of these columns a label. So I'm just inputting the information and then clicking on the cell that I want to be in, and then hitting enter to enter that value. I could also do an arrow over left, right, up, down, and then units, okay? So the first variable that I'm going to put here, and I'm just going to use my example, is I'm going to put OD, okay, for outside diameter. And my units for that are going to be in inches. Then I'm going to put in ID, capital I, capital D. That's also going to be in, whoopsie, inches. Then the next thing I'm going to input is going to be my torque. You can write these out if you wanted to too. I'm just going to, for the sake of just time, I'm going to use the variable letter. And that needs to be in pound, feet, whatever they are in the example, okay? Then I have G, and that's going to be in PSI, okay? Now, down here are going to be my outputs. So, oh, I also have to add length, sorry, and that's going to be in, whoopsie, feet. So down here are going to be outputs. These are going to be the ones that are calculated for me. So these I'm going to enter in, and then down here is where I'm going to write my equations in these right here in that middle column. So the first one I'm going to do is going to be J, polar moment of inertia, and I know that's going to be in inches to the 4th power. Now, if you want to make this a superscript, how you do that is when you're in here, you can either highlight it up here or you can highlight it in here. You're going to go to Font, arrow down, and it's going to come up with this table. And you're just going to hit superscript. Okay, and you'll notice that it puts it as a little 4 above like that. Okay, so again, here, highlight just the number, the little arrow here next to font, superscript is what you want. Okay, just for that one. Otherwise, if you continue to go, then it's going to, or whatever you highlight, it's going to do that same effect. So I'm going to have my J. I'm going to have my, now I don't have my, I'll show you what I'm going to do to make this tau, and I'm going to put OD and tau, capital T, ID. But I am going to highlight this, and I'm going to put it in italics so that it's not torque. It's my torsional shear stress, or you can write it out if you want to. I just don't know where the Greek letter is for it at the moment, okay? You can search for it. I'll let you do that. Just for time's sake, you can put it in there if you want to take the time to do that. Or, like I said, I'm going to do italics. And then I want this in PSI, and then angle of twist, and that's going to be in degrees, okay? So I am going to start off by putting my equation in for my J. I'm going to go back to this line that I determined, okay? So as I look at Excel, I select that cell first, and I start by hitting an equal sign. Now I'm in like writing an equation mode. Then I'm going to start with a parentheses, 3.1415, times parentheses, and again I'm going to write it the way on one line that I showed it there, parentheses. Now DO, my outside diameter, is a cell designation, and that's going to be up here. Now I could either put in C4, or I can simply click that cell, and you see how it recognizes it, and it's going to input it, and then I can continue on. Then I'm going to do the power. Now this is the shift 6 key to the 4th power. Okay, and then I'm going to do minus the ID, which is here, C5, to the 4th power, closed parentheses, and then closed parentheses one more time to get it as the top line, and then divide by 32. And then once I hit enter, I get 0. Why did I get 0? I have nothing in my cells. So let's see. I'm going to put 6 up here, enter. Put 4 up here, enter. I get 102.1. And if I look in my book, let me see where J is. They may not have shown the actual number, but that looks like a familiar number to me, so I'm not worried about it. Yeah, I'm pretty sure I'm good. Okay. So there's my J. Now I'm going to put in my tau max, and I'm going to do the same thing. I'm going to start with my equal sign to get it in that mode of an equation, and I'm going to do parentheses, parentheses. The first one here is the torque. So I'm going to click on the cell where I'm going to put torque in. Then it's going to be times 12, close parentheses, times parentheses, outside diameter, divided by 2, close parentheses, divided by J, which is going to be what I just calculated, that middle one there, right there. And then enter. Here it says 0 again because I don't have a torque in there. So my torque is 20,000. There we go, 7,051. Sounds good. Yeah, 7,060. They did a rounding. Then my G, I'm going to input my G right away. We said that G from the problem was 12 6 zeros, and then I'm going to put the 15 feet in here. So now let's do the ID, torsional shear stress. So it's going to be the equal sign again, parentheses, parentheses, torque times 12 to get it into pound inches, close parentheses, times, another parentheses, DI, the inside diameter divided by 2, close parentheses, divided by J again. Enter. 4701. That looks good to me. Then lastly, I need to do my angle of twist. That was the long one that we had. Okay, so looking at that, equal sign, parentheses, 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 3 of them at the beginning there. Starting with my torque times 12, close parentheses, times, this time it's going to be the length, times 12, close parentheses, divided by, parentheses, G times J, close parentheses for the entire thing. Now this is, after this is going to be my conversion for radians, times, parentheses, 360 divided by 2 divided by, I'm going to see if this works, 2 times 3.1415. I think I need parentheses. I know I do. Parentheses, and then 1 here, and then the closed. Okay. Enter. 2 degrees. 2.02 degrees. Worked. Now, you'll notice that it kind of holds decimal places. It doesn't put the commas in. To kind of pretty this up, I'm going to show you where you want to go. First of all, sometimes I like to have all of my things centered on the column. So if I highlight everything, so it's just kind of starting here, dragging, and then releasing, I've highlighted the items in that column, I can do everything to be justified to the center, okay, right up there. So now they're all in the center. The next thing I can do is I can add decimal places to thing if I like. So I'm going to maybe for these first 2, I'm going to highlight those 2, and then I'm going to right click. And when I right click and I go down to format cells, I have a lot of options here, and you can play around with this. But if I go to number, right now it's set at general. I'm going to go to the number of decimal places. I'm just going to have 2 of them. I'm just going to hit enter. So now it looks more, like normal, like 6.00. Then for the torque and for the G, I'm going to do the same thing, right click, format cell, and I'm going to go to number, but I'm going to add the 1000 separator because otherwise it just looks like how many zeros do I have there? Do you see that? The feet I'm just going to leave like that because that was just a regular whole number. And then I'm going to do the same thing down here. I'm going to center all of, I do have those centered. My J, I'm going to go to number, I'm going to go to 3 decimal places. My torsional shear stresses, they're usually in the thousands. So I'm going to say 2 decimal places there, but then I'm going to put some commas, and then the last one in degrees here, format cell, number of decimal places will be 2. That should be fine. Okay. Now some of the other things that you can do here as well for the cells is you can bold the different text. So if I select the text that I want to do, I can bold it. I can italicize it or underline it, just like kind of a word processor type of a thing. I can also change the color of it, okay? So, as you know, a lot of times this is just kind of going off of my format, I want you to make it your own. My spreadsheets are kind of pretty boring and they're not very fancy. And so I usually have my inputs in blue, okay, and my outputs in green, okay? So I can select whatever color I want, okay? Like that bold. I should underline it too, so it's the same as the top. Then some other things that you can do is you can make it look more like a table, make it look more official. So if I highlight just around these cells and I hit that right mouse button, Format Cells, I can also put borders around these, okay? So I can select the thickness or the type of border that I want, and then I can hit on the side here the different, you can toggle and you can hit it again to toggle it. Enter. And so now I can put like separators there so it looks more like a table. You can put darker lines around the outside, lighter ones on the inside. I'll leave that up to you to play with that. The other thing that you can do is sometimes it's nice when it's like a number that, your final answer, and these are our final answers, which are actually these 3 items right here. Sometimes we want to fill those cells with color to kind of highlight them. And so up here where you see that paint can, this is a fill color. Whatever color is highlighted, and I can do the down arrow and I can change this to whatever color I want, okay, is going to be the fill color. So I'm just going to leave it at yellow there, but it kind of highlights, oh, there's my answer, okay? Again, this is for you to make it as cool as you want, and I expect that. I don't want it to just be stripped down because I want you to kind of play with some of that formatting. So this is, what you would be looking for to finish up that problem to write a spreadsheet for example 12.7. The problem that we're going to look at next, the example problem, which is going to be your homework, is to look at example 12.7. We have a steel shaft with a diameter of 1.75, a length of 3.5 feet, transmits 80 horsepower from an electric motor to a compressor. If the allowable shear stress is 8,000 psi and the allowable angle of twist is 2 degrees, we want to find what is the minimum speed of rotation, okay? So G, the shear modulus is 12 times 10 to the 6th. So we're trying to find our speed of rotation. We're given horsepower, okay? So as we look at that equation sheet that reviews all those equations for chapter 12, we're actually going to be starting down in the corner here. If you recall, at the end of the chapter, we added power is equal to torque times rotational speed. So this is going to be the variable that we need to find, divided by 63,000. The 63,000 takes care of everything unit-wise so that our power is in horsepower, our torque is in pound-inches, and our rotational speed is in RPM. We don't have to do any additional converting because it's done already in the 63,000. So for this equation then, we need to rearrange to solve for our rotational speed. So if we look at that equation, it's going to be N is equal to P times 63,000. Oops, can't see what I'm doing. Sorry. N is equal to P times 63,000 divided by the torque. Okay. Divided by the torque. Now, as we look into what was given in our problem, okay, I have H for horsepower. This should actually be P. Our power is given to us at 8 horsepower. That's good because those are the units for power that we need here. 63,000 is just those conversion factors. And then our torque. Well, our torque is not given, is it? Okay, so this is something we actually have to solve for as well. We're going to have to create a cell to solve for that based on the information. So as we look here, do we have what we need to find the torque? Well, looking back, we do have an equation with torque in it right here, where torque is in the equation for the torsional shear stress. So we are given the allowable torsional shear stress. We could use that right here. We know what the radius to the outermost material is because we're given the diameter. And based on that diameter, we can also calculate the J, okay? So we are going to, and I'm going to leave a little bit of space here, we're going to then take that equation and solve it for torque, okay? So torque is going to be equal to tau allowable times J divided by C, okay? Now we also need to calculate J. We weren't given J, so we have to calculate it based on our dimensions. So we know that J, I'm going to kind of scooch it down here, J is equal to, now this is for a solid shaft, it's going to be pi times d to the fourth divided by 32. So this is pi times the d to the fourth divided by 32. Okay? Now, since we have the equation, so really, where do we start? This is where we end, okay? That's where we end. We need the torque, but we also need the J. So we actually start here, right, with our equation, and then we're going to go to there, and then we're going to go to there. Does that make sense to everybody? So let's write out what our line for our J is going to be equal to. So here's our cell. We're going to start it with the equal sign. It's going to be pi 3.1415 times the diameter. The diameter is going to be an input for us at the top, right? So that's going to be a cell designation, but I'm going to just call it D here. To the, right, that shift 6 to the fourth power. Okay, that is our top line. Parentheses around it, and then divide by 32. Okay. Now that I know my J, and I should put here, this is going to be a cell for the D. Now that I have my J, that's going to be a cell then that we use up here. So let's write out how we're going to put this into a cell. We start with the equal sign. We're going to use the tau allowable first, right, for the top line. Now, as I look, that is going to be a given for me. So this is going to be a cell from my input. Times J, which is right down here, right? That's going to be the cell for the J. Parentheses around those two for the top line. Divide by C, okay? Divide by C is going to be this diameter divided by 2, right? So it's going to be D divided by 2. But I have to put parentheses around it because I needed to do that before it divides in. So again, this is going to be another cell. And then the last one, move up here. Now we know what our torque is. We have a power for an input, and we'll be able to solve for that rotational speed. Oh, I forgot. Oh, wait. Yeah. What didn't we use here? I forgot. What didn't we use? There are two conditions present, aren't there? There's the allowable stress and our angle of twist. If we go right to, and we use this one for the rotational speed, then for torque, then what's going to happen is we're going to not take into consideration that angle of twist. So we actually need to solve for torque in the angle of twist equation. So the angle of twist here is the torque in here. We need to rearrange this to solve for the torque. And then we're going to compare the two torques and use the smaller of the two for the problem, because sometimes, depending on the conditions, one might dictate it and the other one might. So we have to check them both. So So we're going to call this step number 3, and then back to step number 4. So if our angle of twist, the torque for that angle of twist equation is going to be angle of twist times G times J divided by L. So here, it's going to be the equal sign. Now, angle of twist has to be in radians, okay? So down here, we know that our angle of twist is 2 degrees, right? We need to convert that to radians. We know that there's 360 degrees in 2 pi radians, right? Okay? Now, this is going to be our angle of twist, our degrees, but we have to add onto it this portion. So, to do that, parentheses, angle of twist, times 2 times pi, 3.1415, okay? Parentheses, divided by 360s, and then parentheses around both of those. This gets that angle into radians, okay? We can't have degrees. Then we're going to multiply by G. Then we're going to multiply by J. And again, G and J are going to be cell designations. This is my top line now, so I need one more parentheses. And then I'm going to divide by L. Now, in this problem, L is given in feet, right? So I've got to take L times 12 and put parentheses around both here. Now, I'm going to call this T1, okay, and T2. Once I get my values for T1 and T2, I will use that for the smaller of the two is going to go in here, okay? It's going to be an input that we'll put in the problem, and you'll see how we do that. So here, whichever one we end up picking, this is going to be an equal. Our power, which is going to be a direct input in horsepower, times 63,000, parentheses, divided by whichever torque that we end up picking, okay? All right, now we're ready to put it into our Excel spreadsheet. Okay. So let's open up Excel, a fresh sheet, and I'm going to start by my input data. So variables, inputs, and units. So my first variable here, I'm going to just kind of start at the top, diameter, inches. And then I'm going to be length, feet. Then I'm going to be power, horsepower, T-A-L-L. I'm just going to make this like I did earlier, just put it in italics. And that's going to be in PSI. And then over here, G, PSI. Oh, and then angle. And that's going to be in degrees. Okay. All right, so I'm going to put those values in right away, because that way when we're inputting, we can kind of check it as we go. Length, 3.5, power, 8,000, 12, 1, 2, 3, 4, 5, 6, and 2. Okay. We can worry about the units. Okay. Now, this is going to be our outputs down here. And the units. So the first one that we have here, we're going to do polar moment of inertia, J. So equals, so I'm going to put it in exactly the way we had it. So 3.1415 times, oopsie, time, Totally doing the wrong one. Times, this is my diameter, so I'm going to click up on the 1.75 divided by 2, parentheses, divided by 32. Enter. 0.09. Now I'm not sure. Oh, it's supposed to be 0.9. What did I do wrong here? Let's try that again. 3.1415. C divided by 2. Cells. Number. Oh, I know what I did wrong. I did not take it to, let me see here, d to the 4th power divided by 32. So d to the 4th power, there we go, divided by 32. That's where it is, 0.92. Good. And that is going to be in inches to the 4th. And again, to get that superscript in there, we do this, superscript, and OK. All right. The next one I'm going to do is going to be my torque. I'm going to call this T1, torque 1. And this is going to be based on the allowable stress. So here again, equal sign, parentheses, tau allowable, times J, which I just calculated, parentheses, divided by C, which is D, the diameter, divided by 2. Parentheses around the diameter divided by 2. Enter. So 84.18, and that's going to be in PSI. Then I'm going to do torque. No, it's not. It's in pound inches. Okay. Then I'm going to do torque 2. This is going to be based on the angle of twist. So I could put on here allowable stress, and this is going to be allowable angle of twist. And you can make that pretty if you want to. So this one is going to be the equal sign. That was the last one that we did. So it's going to, it looks like I have 3 parentheses to start. It's always nice to kind of write it out first. Now, angle of twist that I have here is going to be 2 times 2 times 3.1415 parentheses divided by 360 parentheses times G times J close parentheses divided by parentheses length times 12 close parentheses. Enter. Okay, so 9.18. Okay, good. And that's going to be in pound inches. Now, this is where I need to make a decision. I need to determine which one of these torques I'm going to use that's going to dictate my design. So, since I have to pick the one that's allowable, I have to meet both conditions, I'm going to hit the allowable torsional shear stress first at a lower torque. So that's going to dictate my design. All that means is I'm going to have less than 2 degrees of angle of twist over the 3.5 feet. So now this is where I'm going to say torque actual. And you need to put that number in. You need to pick. So this is going to be 8418.24, okay? And this is going to be pound inches, and you have to pick the smaller of T1 or T2, okay? So this is going to be an input. This is not a calculated value. So now my rotational speed Now I'm going to go up here, I'm going to double click, and this is going to make it as long as it needs to be. My rotational speed, this is N, capital N. This is going to be an RPM, is going to be based on this torque. So I'm not going to pull one of the torques from here. I'm going to pull from this torque that I input manually based on the decision I make between these two. Okay? So this is going to be equal, and it's going to be, whoopsie, postpone. Parentheses, this is going to be the power. So I'm going to do the 8 times 63,000, parentheses, divided by the torque that I just inputted. Enter. And it looks like I'm off by decimals. Let's see what I did wrong here. 63,000 times power divided by 8418. Yeah. I'm getting 5986. I should get 599. What am I doing wrong?
Isn't the power supposed to be 80 also?
What was that?
Isn't the power supposed to be 80? Not 8? No.
Oh, is that what I have? It was at 8? I have it written as 8 here. Thank you. 80. That will make a difference. Then it's okay, because I'm like, I think my equation looks good. Now, after I do this, I can then adjust my decimals. Remember, I highlight my cell, right-click, format cell. I go to number probably, I don't know, 0. Just because RPMs are RPMs. You don't go to point something RPMs. We can center this on the middle. We can make this all green so that they're all the same. And then we can highlight this bottom one if we wanted to and say, oh, that's our answer, and then make it pretty, okay? So those are kind of the basics. This is like minimum stuff. I do want you to add some nicer looking pretty things by working with that right-clicking format cells. Notice that not just the numbering scheme here, but there's alignments, different fonts. Here's the borders that you can put around, the fill colors. So play around with it so it makes it look like a really nice, cool type of a spreadsheet that somebody would want to fill their answers in and have fun doing, okay?